You may recall that there were two primary factors we could use to analyze the performance of the aircraft in a climb. Those factors were the angle of climb and the rate of climb. Having completed the gradient and angle of climb section, let's now focus on the rate of climb. The rate of climb is the vertical speed of an aeroplane measured in feet per minute and shown in the cockpit by the vertical speed indicator, or VSI. Another way to consider the rate of climb is to see it as the velocity of the aeroplane along a gradient. Let's assume that two identical aircraft have the same angle of climb, but the one on the right has a faster speed along the gradient. Notice that over a given time, the aeroplane on the right climbs through a higher vertical distance than the aeroplane on the left. Therefore, the aeroplane on the right has a higher rate of climb. This demonstrates that forward speed is an important factor in the rate of climb. Nevertheless, if two identical aeroplanes have the same forward speed, but the aeroplane on the right travels along a steeper angle, in a given time, the aeroplane on the right climbs through a higher vertical distance than the aeroplane on the left. Therefore, the aeroplane on the right has a higher rate of climb. This demonstrates that angle of climb is also an important factor in the rate of climb. From this simple demonstration, it can be seen that the rate of climb is a function of both angle of climb and the speed along the achieved gradient. Let's return to the formula for the gradient of climb, which is shown here. The gradient is given by the formula thrust available minus thrust required divided by weight. All that is needed now is to add the velocity function, as is shown here. This is now the formula for the rate of climb. However, there is a little more detail to explain. The velocity in this case is true airspeed. Thrust and drag are both forces. Velocity is distance over time. Force multiplied by distance gives work. Work divided by time gives power. This means that instead of thrust multiplied by velocity, the formula now contains the expression power available, and instead of thrust required multiplied by velocity, the formula now has power required multiplied by velocity. The formula now reads power available minus power required, which gives excess power, divided by weight. For any given weight, the greater the excess power available, the higher the rate of climb. Conversely, the lower the excess power available, the lower the rate of climb. In order to maximize the aeroplane's rate of climb, therefore, we need to maximize the excess power available. Shown here is a graph of power available and power required for a typical jet aeroplane. In order to provide a benchmark for the next part of the lesson, it's necessary to locate the three reference speeds we mentioned earlier in the lesson. The speed found at the bottom of the power required curve, shown here, is called the velocity for minimum power, or VMP. There was another speed, slightly faster than VMP, called VMD. This speed is the velocity for minimum drag, and it's found at the tangent to the power required curve. Lastly, the highest of the performance reference speeds is 1.32 VMD, which is located at a point beyond VMD. Having analyzed the reference speeds, the object now is to locate where excess power available is maximum. The area between the two curves represents the area of excess power. The greatest amount of excess power available will be found where the distance between the curves is at a maximum, as shown here on the graph. Notice that it occurs at this speed. At any other speed, the excess power is less, and the rate of climb will be less. The speed for the best rate of climb is called Vy. For a jet aeroplane, you'll notice that this speed occurs at 1.32 VMD. Vy is the airspeed to use to climb to the cruise or en route altitude, as it will give the greatest height gain per unit time. For a typical 737-400, this speed is about 275 knots, and is usually published in the aeroplane flight manual as an indicated airspeed. Shown here is a graph of power available and power required for a typical light aircraft. On the graph, the greatest amount of excess power available will be found where the distance between the curves is at a maximum, as shown here. At any other speed, the excess power is less, and the rate of climb less. As we've already learnt, Vy is the speed for the best rate of climb. For a propeller aeroplane, you'll notice that this speed occurs at Vmd. It's important to remember where Vy is found for both jet and propeller aeroplanes. For example, looking at the graph, it can be seen that if a propeller aeroplane were climbing at a speed equal to Vmp, and then selected a slightly higher speed, the excess power would increase, and the rate of climb would increase. It's easy to see how speed changes affect both excess power and the rate of climb when the graph is used. Be aware of what the graphs look like, so that you can use them to your advantage in test situations. Let's now examine what factors can influence the rate of climb. The first of these factors is aeroplane weight. You'll recall that an increase in weight creates more weight-apparent drag, which reduces the angle of climb. For any given airspeed, if the angle of climb reduces, then so will the rate of climb, because they are both fundamentally linked. Weight has a further effect, though, that we've already talked about. An increase in weight will require an increase in lift. Increasing lift increases induced drag, which causes the drag curve to move up and to the right. The power required curve, shown in red, is actually based upon drag. Power required is drag multiplied by velocity. So, if the drag curve moves up and to the right, so will the power required curve. This results in less excess power available, and therefore a decrease in the rate of climb. The power graphs for both jet and propeller demonstrate this. However, it's important to see that the speed for maximum excess power available is no longer what it was. It's now higher. So, with higher weight, the rate of climb is decreased, but Vy is increased. The next factor that affects the rate of climb is the configuration of the aircraft. In other words, the use of flaps and undercarriage. If the undercarriage and flaps are deployed, then the profile drag of the aeroplane will increase. This increases total drag, and the drag curve moves upwards and to the left. The power required curves will follow the same movement as the drag curve. Notice the reduction in excess power available as is shown by the blue double-headed arrows. You may recall that a reduction in excess power reduces the rate of climb of the aeroplane. However, the important effect here is that the speed for maximum excess power is no longer the same. It's now lower. So, with the undercarriage and/or flaps deployed, the rate of climb is decreased, and Vy is decreased. If you use flaps for takeoff, remove them in stages when you've attained a positive stable climb, ensuring that you check through the aeroplane flight manual for the correct actions for your aeroplane. As you retract the flaps, the rate of climb and the speed to attain the best rate of climb will increase, so you should accelerate to ensure you remain at Vy.